Welcome back to our continuation of Chapter 6 in Physics 20. Today we're going to look at 6.2, which is going to be talking about springs. So what a spring is it's a circularly wrapped material that is going to stretch or compress, and the big important part here is that it's going to return to its original position. So after we apply a force on it, it's going to apply a force back to get to where it was originally. So if we have a spring like this, we can either apply a force on each side to compress it or make it shorter like this, that'd be in a compressed position, or we can pull it apart and apply a force in that direction to have it stretched in that position. When it's up here and there are no forces acting on it, that's called equilibrium, when there's no net force. That's where the spring just wants to sit naturally. And when it's in these two positions, we've applied a force to it and it's got some potential energy stored up in there because it wants to move and go back to its original position. So that's when it has some potential energy stored in it, and this would match elastic from what we looked at in the previous lessons. And before we get into energy, we're going to look at the forces that are acting on a spring. If we take a spring like this that's in equilibrium, and we're going to apply a small amount of force in this direction, and it's starting off at this length, it's going to compress a little bit to that position. So a small amount of force here is going to cause a small distance that it's going to compress. However, if we take another spring, or the same spring there, and we apply a much larger force, and it's starting right here, we're going to get a much larger compression, or a much larger distance that is going to compress. So this might be kind of intuitive that the force and the distance that it compresses are going to be related to each other. More force causes a further compression. But this isn't the same for all springs. Say we took two separate ones like this and we applied 20 newtons of force to each spring, and again they're starting right here at that position, then they might compress different amounts. This one only moves a small distance, where this one moved a large distance. And that has to do with a characteristic of the spring and how hard it is to stretch or compress. They're not all equal. So this is relating to how many newtons it requires to compress it 1 meter. So we measure this in Newton meters, and it's called the spring constant, and we represent it with the letter K. So putting those two ideas together, the force is related to the spring constant and the distance that it's going to be compressed. And this is our formula for force on a spring. F is equal to kx. Now I realize that we have x instead of d. It does mean the distance that is going to be displaced, but we use an x in this formula to represent that value. Just going to throw the units in here. Force is going to be measured in newtons, k is going to be in newtons per meter, and then x is going to be in meters. All right, so we get newtons per meter times meters, and that gives us newtons on this side. Not too hard a formula, but let's do an example with using this. So let's say a 20 Newton force compresses a 30 centimeter spring to 20 centimeters. What is the spring constant? Okay, so we start with force is equal to kx, and it was originally 30 centimeters when it's in equilibrium, then it goes to 20 centimeters. So that means it's compressed 10 centimeters. And that's what we're focused on. So that's going to be the x there, how much it's changed, and we're trying to solve for k. So we're going to divide by x on both sides, take the force of 20 newtons, divided by our x. Now it does say 10 centimeters here, but we do have to measure it in meters like we saw from the previous slide. So this is going to be 0.10 meters. Important to change that unit, and we get a value of 200 newtons per meter for our spring constant. Based off the units, I guess would be 2.0 times 10 to the 2 newtons per meter as our answer. So not too hard to calculate that, but the chapter is talking about energy. So what about energy in a spring? We already said it was potential, but how are we going to calculate that? Well, we know from before that work is equal to force times distance, and work is looking at the amount of energy change. So if we put a certain force into a spring, based off how much it compresses, there should be amount of energy change in that spring. Okay, so if we're looking at the force that's going to be applied to the spring, we would think, okay, well, force is equal to kx, and so I just need to plug that in for the force that I apply, and we would think it would be work is equal to kx and then d. This is an x and that's a multiply. Maybe I should just change that to a circle. F times d, and this is k times x times d. However, it is a little bit more complicated than this. If it starts right here and I apply the force that it takes to compress it to go right there, a very small distance, is a very small force. All right, really, really small. You can think of the first little bit, if you're, say, pushing it 10 centimeters, the first millimeter that you compress it requires a very small force. It's really easy to compress that little bit. But yet later on, as I compress it further and I get all the way to here and it's gone this distance, this requires a large force. All right, so if what you're doing is you're trying to get to here from this position, you start with a small amount of force, but you end with a large amount of force. So this number over here isn't consistent. It's going to be changing as the spring compresses this way. So we can imagine, think of like the smallest distance. As this approaches like a millimeter, then a tenth of a millimeter, then a hundredth, this number is going to approach zero. So you can think of the first tiny little bit requires almost no force, and the end requires our maximum amount of force. So since that's changing, what we're going to do for finding the work is take the average amount of force as we're compressing the spring. So how we would do that is we would take the force at the start plus the force at the end and divide by 2. That'd be our average force during the compression. But as we said, it's approaching zero as we get to the very start of when we start compressing it. So that's going to make this term 0. So then we're going to take our final force, how much it is at the very end, that large amount, and just divide by 2. So I'm going to write in now here for our work equation, it's going to be work is equal to the average force, so half F times D. Okay, now when I put that force in, it's going to be for that maximum compression there, so it's going to be half our spring constant times the maximum compression times the distance that it compressed. Now we notice that this x is the same as this distance, right? It's this amount that it gets compressed from here to here. It's the distance that we're applying that force, and x is also the compression of the spring. So we're going to make that the same value. I'm going to switch this d to x because it's the same thing. And so we have half times k times x times x. And this is half kx squared. And that's the formula that we're going to use. So just to recap, the distance in the work equals force times distance, and the x in F is equal to kx is the same value, because that's how much the spring is getting compressed. And then we're adding in the half because we're averaging the small force at the start and the large force at the end. So that's why we end up with this formula, and it looks on your formula sheet like this, is EP, because this is potential elastic energy, and it's half kx squared. Let's just check these units to make sure this does give us energy. K is in newtons per meter, and x is in meters, and since it's squared, this is like meters times meters. Okay, newtons per meter times meters immediately cancels that out, and we're left with Newton meters. What a Newton is we found force from mass times acceleration, so this is a kilogram for mass, meters per second squared for acceleration, times by meters again, that gives us 2 m's, kilogram meter squared per second squared is what we saw from the last video, and that's equal to a joule, which is our unit for energy. So we're just double checking that the units work there, which they do. So let's do an example of this. If it takes 50 newtons to compress a spring 15 centimeters, how much energy is stored in the spring when it's compressed 20 centimeters? So I put this example in because sometimes we have to use the force and the energy formulas together, and this is going to show how we do that. So the question is ultimately asking for how much energy. So I'm going to start with EP is equal to half kx squared. Now I just need to solve for EP. Half is just 0.5. X is going to be the 20 centimeters, but I don't know K. So I don't have all the information. There must be some way that I can solve for K, and the only other equation that we have with it is F is equal to Kx. So let's see if we can solve for this. To solve for K, I would have to divide by X on this side to get K. Let's see if we have both of those. We do have a force right here, 50 newtons, compresses it 15 centimeters, which is my X. So this starting part of the question tells me how to get K. So we'll take 50 newtons, divide by 15 centimeters. Again, remember to turn that into meters, 0.15 meters, and I'm getting a number of 333.3 repeating newtons per meter. That's the first step to find our K. Now that I have that, we can plug it in to this equation, and I'll set EP is equal to 0.5, which is our half, times the K, 333.3 repeating newtons per meter, times X. Now it's asking about 20 centimeters, so don't use that 15 again. This is how much energy when it's 20 centimeters. So let's put in there 0.20 meters squared. And we put that in our calculator. I'm getting 6.6 repeating joules. That would round to 6.7 joules. All right, not that high because the distance is in meters, and when you square that, it becomes a pretty small value. So 6.7 joules for that one. Lots of questions are going to look like those, using those formulas, but there could be some that also involve gravity. So I wanted to include one more example like that. It says we have a 50 centimeter long spring, looks like this, and it's hanging from the roof and it's in equilibrium. So the net force acting on it there is 0. It's in a steady state there. But then it says with a 2 kilogram mass, we should have said that in there, 2 kilogram mass is hung on the spring. It stretches to a new length of 80 centimeters. What is the spring constant of the spring? Okay, so we start off at this position in equilibrium, and then when we put a mass on it, it's going to stretch to a new length. What is the spring constant? So the easiest way to solve this is that there is a force being applied to the spring, and it's stretching a certain length. So we're going to focus on the force equation, and that's force is equal to kx, and try and solve for that k. Now the thing that makes this a bit harder is it doesn't say like 50 newtons is applied. So how do we figure out that amount of force? Well, the force that's being applied to this mass is Fg. And we know how to calculate Fg. It's equal to mass times gravity. So if we put mass times gravity is equal to kx, we should be able to solve for k. We'll divide by x on both sides. Our mass is 2.0 kilograms times g, which is 9.81 meters per second squared. And the x is the amount that it stretched. It went from 50 centimeters to 80 centimeters, so that's 30 centimeters. We need this in meters, 0.3 meters, and we should get our answer there of 65.4 newtons per meter. Because we have 2 digits in the question, that would round to 65 newtons per meter as our answer. Okay, so I gave you a couple more examples in the presentation there. I hope that helps you to do the practice questions. Do give them a try, and I will see you in the next video.